or this triangular area that is actually expanding. It started here and then it started to become bigger here. This is velocity 6.61 meters per second, and it's sitting in this field of the magnetic field. Now we're asked a couple of questions about this. So the first thing is give me the flux at time equals 2.69. So let's try to figure that out by looking at the flux equation. Suppose we'll say the integral of b dotted with the dA. And we know that the A is actually changing here, the area. So let's figure out an equation for that area, I suppose. Essentially what's going on is we're coming up with this new length over here. I'll call this length y. And I know that if I want to travel that much distance, I can go y equals vt. So now I have an equation for this line here. And then it's all about this little angles thing. Because we divided this particular line in half, I know that this is 45-degree angles. This actually was already 45-degree angles. So now that this is actually a smaller version of that previous triangle, I got 45, 45, 90 here. So if I want to find the area of this thing, it's going to be y times, this is actually another y because it's the same length, same angles. And then this is going to be like y squared to 2, right? But it's just going to be y times y divided by 2 would be the area for one of these. But guess what? If I move this over here, rearrange this, this actually forms a square over here. So technically, if I just find y times y, I've got the area of the whole triangle. So it's basically just y squared. And so we have this formula here for the area. Now, that's essentially what the integral of dA equals. It's going to be v squared t squared. And this is, it's okay. So let's just go ahead and figure out what b is. B is, we'll kind of just say the flux. We could actually figure out what the answer is here, because we got 0.491, and then we're going to multiply that by v squared t squared. So it should work. We would say 0.491 times the v squared is just going to be 6.61 squared times the t squared is 2.69 squared, and that should give us the total flux at this point. So the flux is 155 to 35. I suppose this would be in Webers. And then for the EMF, isn't that just going to be the negative time derivative of this? And since we have a t component to this, technically we would just take the derivative of the area over here. So let's figure out what that would be. If we have v squared t squared, and we're trying to take the derivative of that, and probably doesn't really, we don't care about the negatives these days. It's just magnitude. We'll say time derivative is 2v squared t. And what's the EMF? We still need to have the b component to this because 0.491, that is what the EMF is. It's just the time derivative of this. So now we can plug that in there. Get our answer 2 times 6.61 squared times 2.69 times the 0.491. And now the EMF is 115.42 or so volts. And over here, notice how they're asking for what's the exponent on the time. Exponent on the time is 1. So n equals 1. All right.